Okay, good morning, everyone. So let's get started. Do you have any questions or anything? All good? All right. So let's pick up from where we left off things last time. So last time we were discussing, yeah. So I will assign homework on Friday, I guess. So homework and due next Friday. So I guess homework of this week will include whatever we covered so far that has not been on the homework. So yeah, it'll come on Friday. So there's like a 1 day difference, but that's to make up for the exam, time. Oh, so I'm not sure if that's what you're asking. So there's nothing due on Friday. Yeah. So this Friday, right? There's no homework due. There'll be fresh homework this Friday, due next Friday, if that's what your question was. Yeah. All right. So we were somewhere in 10.3, but the point is we were discussing Chimera lower bound. And it goes like this. It says that if theta hat, right, is unbiased for theta, okay, then the variance of theta hat is no less than 1 over n times in the information, where the information, this is the Fisher information, which is equal to expectation, right, of the derivative of the log square, which also is equal to the minus of expectation of the second derivative. Okay. And so what we'll do today is we'll try to kind of illuminate this kind of relationship, and also explain why Chimera lower bound is true. Okay. So we did like a bunch of examples last time, right? So today we're just gonna go over the ideas of the proof and some of the mathematics in between. All right, so where to start, right? Where to start is kind of like, let's try to explain why. Okay, the idea of Chimera So at first, when you look at this, I think it may be a little bit mysterious on how you can possibly, right, bound the variance of some random variable from below. Okay. And this quantity also, if you look at it, it probably is a little bit mysterious. All right. Why take the log and take the partial and then square, etc. Right. So there are a lot of mysterious things going on here. But first of all, let me say this, and it will be fundamental. Is a fundamental relation okay in the Chimera bound business is this. that first of all, the expectation of this quantity, okay, without any square. So it's just the expectation will be 0. And so therefore, this right here with the square, right? So this is a random variable, right? And I believe this is called the Fisher score, but don't quote me on it. I think it's a Fisher score, okay? But basically, this, if you want to call it a Fisher score, this is a random variable, okay? Because this big X here, remember from last time, is not a sample value, right? It's a generic random variable that has the same distribution as the population distribution. So anyway, right? This Fisher score has expectation has mean 0. So therefore, of course, the second moment, right? The second moment then would be the variance, right? And of course, we call that the Fisher information. So the Fisher information is nothing but the variance of the Fisher score, okay? And so the point is then when you look at this, the Cromero lower bound is not that mysterious because it was relating a variance of something with a variance of something else, okay? So it relates the variance of the estimator with the variance of the Fisher score. Now, what is this n doing? Okay, why the n? Of course, the n is a sample size, right? The n is a sample size. And then, so you note that these are two fundamental relations that you should keep in mind. Then you observe that, right, in general, our likelihood function is a product, right? Our likelihood function is a product of individual density function, for example. So when you take the log, as we usually do, then you got the sum of the log, right? Which, right, this single guy is the representative of all of these because these are all the sample, right, values which follow exactly the same distribution as the population. So if you take the variance of the log likelihood, because the sample is IID, right? Because the sample is IID, this will be the sum of the variance because they're independent. And because they're IID, all of these guys are equal. And so you can write it as one single variance. And of course, that's just n times the Fisher score, Fisher information. All right. So from these two observations, you get that the denominator, right, of the Cromero bound is just the variance of the log likelihood of your sample. Okay. The denominator of the Cromero bound is the variance of your log likelihood. So that's that mysterious quantity. So, right, so the Cromero bound says then that the variance of theta hat is bigger or equal to 1 over, right, the variance of the log likelihood. Okay. Now it's less mysterious maybe because it says that, right, the variance, the product of the variance is bigger than 1. All right, so maybe a little bit less mysterious, but still, why would the product of two variants have to be bigger than or equal to 1 in this case, right? Of course, there's some special thing going on here with this number 1, 2, but when we get it down to here, is there any fundamental kind of probabilistic quantities that you can think of that involve somehow the product of variances? Any quantity in probability you can think of that involves product of variances. Anything comes to mind? Well, let me remind you the correlation. Right. So actually, first of all, do you know, is there anything that naturally happens with the correlation? What is the natural bound on the correlation of two random variables? Yeah, or we would say, right, the absolute value of the correlation, maybe I'll just do 1R, right? Correlation, the absolute value of the correlation between any two random variable is between -1 and 1. Oh, sorry, so absolute value is less than or equal to 1. Okay. What that says, right, is that this quantity right here is less than or equal to 1. Now the variance being positive, right, square root and everything, what does that say about the product of the variance? Like that. Yes. So comparing, sorry, there's a square here, right? So comparing, right, these two inequalities, you see that somehow this one here, right, the one on the numerator of the chimeral bound is just the covariance between these two quantities. This right here is the covariance between these two quantities. And the chimeral lower bound is just a way to rework the correlation bound. Okay? The chimeral lower bound is just a way to rework the correlation bound. So because you know the correlation between two random variables is between -1 and 1, you write down, right, what the correlation is, and you bring the variance on one side, and then you have it somehow, right? So the miraculous thing with chimeral, if you want to say, is somehow that the covariance term is 1. And I'll tell you that it's not usually 1, okay? It's 1 because this is unbiased. That's where unbiased comes in. The unbiasedness of the theta hat makes this into a 1. Otherwise, it won't be 1, okay? So to recap what we pointed out, okay? This is your chimeral bound. First of all, right, this whole quantity is the variance of the likelihood function of the log likelihood, okay? This is a variance of the log likelihood. And 1 is the covariance of theta hat and the log likelihood. And so we will go ahead and show you why this is true, why this is true, why this is true, and why the covariance is 1. Okay? Any question on this? All right, so to make things easy, okay, we will assume we show the computation for n equals to 1. Okay, so just to make things easy, when the general sample size is n, the computation is actually the same. Most of everything carries out in the same way. So what do I need to show you? First, right, so there are several things I want to show you. The first one is that the covariance, right, between theta hat and the log likelihood, the derivative of the log likelihood, like this, will be the derivative of the expectation. Okay, so that's the first claim. So generally, okay, generally, this is the covariance term. But because you assume, right, we assume that the theta hat is unbiased. Therefore, this term will become theta, and that's why it's equal to 1. But in general, it doesn't have to. In general, it's this. So actually, you do have, right, we do have a Cramér bound for bias estimator. If theta hat is biased, we can still have a Cramér bound on it. Okay, so but for comparison purpose, we just assume that this is unbiased, and we look for the minimum variance among the unbiased estimator. Okay, but in general, it works for biased case as well. So how does the proof go? Okay, how does the computation go? And by the way, right, because I assume the sample size equal to 1, the log likelihood of the sample reduced down to 1 case, and that's why it's this. Otherwise, right, it'll be a sum. All right. So the covariance of any two random variable is the expectation of the product minus the product of the expectation. Okay. And so here you see this term, that is the expectation of the Fisher score. That is exactly this claim right here. I claim that the expectation of the Fisher score is equal to 0. So to finish this claim, I'll actually have to touch this term as well. So we'll do the second claim right here, right? So claim, I guess, 2 is expectation of the Fisher score is equal to 0. Okay. And once I do this, I will plug it in and just handle this term. All right. So how on earth, right, is this equal to 0? Well, the expectation of any random variable will be, right, the integral of this against the density. All right. And so here you see the reason is this random variable is on the population distribution big X. That's why, right, we just replace big X with small x and integrate over all density, right, over the density of over all little x. But when you write this out like this is a log of a function, right? This is a log of a function. This is a log of the density itself. So when you apply chain rule to this, it becomes the derivative of f over f. Sorry, right? This is all f. So maybe let me just not even write this. This is just f. Like that. So the derivative of the log becomes 1 over f times the derivative of f. And then there's still the density itself. Okay. And so you see what happens. These two density cancel. And you get okay. Any questions so far? Okay. So how is it that then this term somehow is 0? Right? Because that's what we're claiming, right? We say that the expectation of this random variable is 0. When we write down what the expectation is, it comes down to this. So how is it possible that this term is equal to 0? Well, so here's something that you don't usually do in your calculus. Notice that this is the integral with respect to dx, right? This is the integral with respect to the x variable. The derivative is respect to the theta with the parameter. So in many cases, if the condition is satisfied, you can exchange the integration and differentiation. Okay. So this is just like a generalization of this rule. You can exchange derivative and the sum. Okay. When you have like the sum of derivative, it's pretty obvious, right, to take the sum first and differentiate, or sum the derivatives, right? With the integral, it's the same way, except that you have to make sure that some conditions satisfied, which is good here, so we don't have to check that. Okay, so we bring the derivative out. All right, but after you take out the derivative away from the integral, what is this term right here? Correct, exactly, because this is density. That's exactly it. That's the key. So that's why it's equal to 0. Okay, so that's why it's equal to 0. So therefore, right, the expectation of the Fisher information, the Fisher score is always 0. All right. So that means, right, in the covariance calculation, this whole thing disappears. We just have to worry about the cross term. Okay. So we only have to worry about cross term. Any questions so far? All right. So now let's go back to 1. So for one, we only need to calculate then the cross term. Now, how do we do this? It's the same way. Theta hat, right, is a function of x because theta hat is a statistic, right? It's an estimator. So this is, you see, this is where there's certain kind of assumption we use implicitly. Theta hat is a random variable based on x because we have a sample of size 1, right? Statistic only depends on the sample. So here, the expectation of this will be the integral of theta hat as a function of x, if you will, times this. And then times the density. So maybe let me write it down here. Right? Just exactly like what we wrote up here. So in a way, actually, you see that the Kerr-Bound investigation follows one trick, exactly, just one trick. The trick is to work out the derivative of the law and then exchange derivative integration. Okay, so do the same thing. Derivative divided by the density. These two guys cancel. And then, right, we bring this out. Now, if for those of you who may wonder, right, what about this term? How can we bring the derivative out over here, ignoring this term? Right? Do you see, is there any issue with that? So before, right, I just bring this out because this is only derivative here and I bring it out. Here, there's one more term, theta hat of x. Is it okay for me to bring the derivative out in front like that? Not worrying about theta hat. Any issue here at all? So I asked this, right, because I think some of you may feel uneasy or confused about this move, maybe, who knows. But again, right, this is where the clarity of whatever we write down matters. This theta hat is just a notation for a function, okay? Remember, right, theta hat is an estimator for theta. Remember what I said, an estimator cannot depend on the parameter itself. Otherwise, it just doesn't make sense. So theta hat here is independent of theta. Okay, by assumption. So, right, the estimator cannot depend on the parameter itself. So therefore, right, as far as theta is concerned, this is just a constant, right? The theta hat dependence is actually on x. Okay, so notation, even though we call theta hat, it has nothing to do with theta directly. So that's why we can bring it out. Okay, it's just a constant. And then after we bring it out, then we recognize that this term is the expectation. Any question? Okay, so there you have it. Actually, at this stage, we have shown everything about Cramér-Rao, because then Cramér-Rao lower bound would just be, right, that you have variance of theta hat will be bigger than equal to covariance of theta hat and the log likelihood. Let me do it like this, okay? In the general case, divided by the variance of the log likelihood. Oh, yeah, that's okay. Actually, it's going to be covariance square. And so we have shown that the covariance of the estimator and the log likelihood, oh, sorry, the derivative, not just log likelihood, derivative. Of the log likelihood. We have shown that the covariance of the estimator and the derivative and the Fisher score, if you will, right, is going to be equal to the derivative of the expectation. So like that. And the variance, right, the variance here, because the log of the product is sum of the log, is just going to be n times individual variance. First of all, like this, right? So going from here to here, what I have reduced is I have reduced the sample, right, from n points, n independent points, to one single point. And then let's keep this term. Because the expectation of the Fisher score is equal to 0, then the variance is going to be expectation of the term square. And there you have it. Okay. And I prefer to keep the term this way, to keep the inequality this way, right? The Cramér-Rao bound you know of, take one more step and say that this is theta. So that's 1. So 1 square is 1. Okay. But I prefer at this stage to leave it like this, because it tells you that, right? So we can have Cramér-Rao bound is also applicable to biased estimators. Okay. So if you want, if you have a biased estimator, you can also use this bound to see whether it has achieved the best variance possible for itself, right? In this sense. All right. So the only reason why, right, for conceptually the book doesn't discuss this, is because it's hard to compare different bias estimators, right? Remember the bias variance trade-off, right? I guess the more bias you pick up, maybe the more variance you can reduce heuristically. So therefore, it's unfair, right, to compare a biased estimator with an unbiased estimator, for example, on the variance, on their variances. So therefore, you want to compare apples with apples. Therefore, you say that, okay, let all these guys be 1, and I compare the variance among this class. But right, in terms of mathematics, there's no reason why this term has to be 1. It can be a generic term like this, where you allow for bias. Okay, I mean, this is not really bias, right? This is just expectation square. If you want to look at the bias, you have to subtract theta from this. But anyway, right, this term reflects the bias anyway. Any question? Okay, so one last thing I need to show you is the last assertion to say that, well, this term, right, remember last time, from the calculation point of view, this is not nice because of the square, right? The square is not nice. It's hard for us to do computation. So we want to do one more step where we claim that somehow this second moment is the second derivative. Okay. And after we show this, then we have completed everything. So how do we show this calculation? Well, guess what? It's exactly the same trick again, right? It's exactly the same trick again, where we write down, right, the expectation of this term square will be the integral of this square times this dx, right? And then we work out the log term. This whole thing square. Okay. Which you see now, unfortunately, right, because it's a square, they don't cancel, right? They don't cancel. So what we are left with is something like this for now. Right? Because this cancel with this gives you one power at the bottom and a square on top. So how on earth can we get down to here? How on earth can this term be equal to the second derivative of the log with the minus? How is that possible? Does anyone see why that is true? Well, there's one more trick here, okay? That notice that this term, you should write like this. Is the partial by itself times this product. Sorry, this ratio. Like this, okay? So I split this square into two terms, right? And then keep this. Why do I do so? I do so because this is gonna be the derivative of the log, right? This term right here is the derivative of the log. So I will write it down one more time as the derivative of the log. Okay. And now this is a little bit more hopeful because somehow I want to relate this to the expectation of the second derivative, right? I want to relate this to the expectation of the second derivative. So does anyone see what the final trick will be to somehow turn this into the second derivative? Well, to turn this into the second derivative, this should remind you of something like integration by parts, right? This should remind you of something like integration by parts, where you somehow integrate this and differentiate this. Okay, that's 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 how you would turn the derivative here to the second derivative by differentiate this. Except that here is not exactly integration by parts, because integration by parts require that the derivative here would be in terms of x. So what we do here is not in the idea of integration by parts, but is not integration by parts, it's just product rule, right? We apply product rule to get us to, right? This is basically, right, the product of derivatives. So you can still write it as this minus this. Okay, do you understand? Because this plus this actually will become this by product rule. So this term plus this term will be this term by product rule. So when I rewrite, right, I just rewrite like this. So actually, it's exactly in the spirit of integration by parts, except that, right, I do not do integration by parts because the derivatives with respect to theta. Okay, but it's just a simple application of product. So I have two integrals to take care of. The first integral is this, and I will sorry, give me a moment here. Oh yeah. So the first term, right, this one, then you recognize it's just the expectation of the derivative of this. And the second one is just the expectation of this. Okay. Because the integral of something against a density is just expectation. But we recognize what this is, right? We know what this is. This is 0 from the previous calculation. Therefore, the final calculation comes out to this. All right. So to recap, right, we calculate the expectation of this square, write down whatever that is, cancel the term, right? Use product rule, rewrite it, recognize this is 0, and then get down to this. Okay. So anyway, the point being is it's a bunch of tricks, but I want to show you why, in practicality, all right, the Fisher information is more easily computed, right? As you saw from the last example. With this formulation, than with the first formulation. So it's just in terms of computation, right? But you should see why they give you the same result, and it's exactly by the previous proof. Any question on this? Okay, so I guarantee you this is one of the hardest calculation that you see in this class. All right, but I do believe you should see it at one point, because if you apply Fisher and if you apply Khmer without understanding where it comes from, I don't think that's good. But anyway, like, you won't be responsible for this kind of calculation, so don't be like super scared. But try to appreciate, right, this as much as you can, and trust me that if you ever go further in statistics, if you want to like pursue higher education in statistics, these kind of fundamental quantities you will see again and again and again. So that's why I want to show you the background of this. But maybe more down to earth for what we want to do in this class are the exceptions to Khmer. Okay. So the question is this: is there any family of distribution where the Khmer bound, as we stated, do not apply? Or maybe it does not apply, right? So in other words, right, it says that if theta hat is unbiased for theta, then the variance is lower bounded by 1 over n, right, times the Fisher information, which is this. Is there any example or any case of a random variable or a family where this quantity does not apply? Any example you can think of? Uh-huh. Very good. Excellent. Excellent. And why you think that uniform fails, or why this is not appropriate for the uniform? That's very good. Excellent. Excellent. Exactly. I think that's a very good way to look at it, right? Because here you are differentiating with respect to the parameter, right, of the density. What is the density of the uniform, right? Let's say the uniform from 0 to A, 0 to B, right? Let's say. So the density, right? Let's say X, right, is uniform. The density is, in terms of B, will be 1 over B, right? And this is where, again, right, a lot of students make mistake because they think, yeah, this is this, I can take the log, I can take the derivative. That's not true because there is a indicator function, right, that x is between 0 and b. In other words, a lot of time, right, you forget the bound, right? This is the bound on the support of the random variable, right? A lot of time, so here's b, right? The density is 1 over b. But then it's 0 outside, right? It's 0 outside. So when you take the log, right, and you take the derivative, this term also is a function of b. Okay, this term is also a function of b, and exactly like Alice said, right? At this point right here, at the point where b equals to x, it cannot be differentiated. Okay, it cannot be differentiated. So because of that, you cannot make a sensible random variable out of the derivative. Okay, you cannot make a sensible random variable out of derivative. And again, if you want to kind of question why it doesn't work, is exactly this indicator function. Okay, so generally we cannot apply Cramero bound in this form to distribution whose support depends on the unknown parameter. Okay. So I think there can still be a Camara style of bound for this case, for example, but it will be a different formula. It will be a different approach. And you have to think about what that form is. So don't worry about it, okay? The message is that if you state it like this, it simply doesn't work for a uniform or for any distribution whose support depends on the parameter. All right. Let's take another example. From your homework, you are given this family of random variables. E to the minus x minus theta over delta, right? I think 1 over delta for x bigger than or equal to theta. Okay, so this is like a scale shifted, right? Scale location family of exponentials. And I mean, on your midterm, right? You're exactly asked to deal with this when delta equals to 1. But so there are two parameters, right? Delta and theta. Okay. So question, right? Can you have Cramera bound on variance of delta hat? And can you have Cramera bound on variance of theta hat? What do you think? Excellent, Christine. So that's exactly right. Yes on the delta and no on the theta. Exactly. Does everyone see why? So yes and no. And again, right, I mean, I'm just being pedantic here. No means the current way we state it doesn't work. That doesn't mean that you cannot come up with a bound, right? That's research, for example. You want to work it out, but in a different way, in a more advanced way, right? But in the current way we stated, no. Okay. Does everyone see why? Because delta, right, has nothing to do with the boundary. In fact, right, you remember roughly what delta should be. Delta hat should be. Delta hat should roughly be x bar, right? If I'm not mistaken, because that exactly is the mean. So x bar here should easily have some kind of bound on the variance. What should theta hat be? Theta hat should be the minimum, right? And the minimum, by the way, is biased, but you can easily correct for the bias, right? So that's not a problem. You can turn into an unbiased estimator. But the problem with the theta hat, right, is because of the boundary. So it runs into exactly the indicator function problem like this. Exactly, Madhav, right? But so I want to distinguish, right? This is a little bit more advanced example, but it's super interesting in the sense that I don't want you as a student, right, in general, confuse this statement, right? So the statement here only applies to whatever that controls the boundary, right? Here, theta controls the boundary. So like Christine said, right? No here, because that's theta hat. But Carmel bound works perfectly fine for delta. Is that okay? Any question on this? Yeah. So if you understand this, you probably get you get the spirit of Carmel and estimator in general. That somehow these things are all connected in that way. All right. All good. Any other question? So one last thing is this is the book doesn't mention this, but I think it's super important too. You'll see this. It's called asymptotic. On MLEs. Okay. Now I'm not sure if you pay attention, if you noticed that a lot of times, right, when we do moment method and MLE method, usually the MLE tends to win out in terms of efficiency, right? I'm not, don't trust me on this, right? It is a very qualitative statement, okay? But the MLE tends to win out. But the MLE tends to be unbiased, tends to be biased, okay? A little bit, right? For example, the min, that kind of thing. But the following basically tells you that the MLE actually is almost optimal in this way, that if theta hat is an MLE estimator of theta, then square root of n theta hat minus theta converge to a normal distribution with mean 0 and variance 1 over the Fisher information. Okay. So let me state right away, right? The exception for this statement is uniform, and anything, like the boundary case, support depends on above, right? So for the case where Cromel round doesn't work, this doesn't work. but because the information depends on the derivative. But if things work, if you can take the derivative and everything, then you see this statement tells you two things. Asymptotically, theta hat is close to theta. So asymptotically, the MLE is asymptotically UMV. Okay. So again, I would want to say under some conditions. Otherwise, you may apply it in the wrong place. But a lot of times, when the derivative works, Chimera bound works, then asymptotically, your maximum likelihood estimator is unbiased. It will actually, it's even better than that. It goes to theta, so it's stronger, it's consistent. Your MLE estimator goes to, its value goes to theta. Notice unbiased actually is weak. Unbiased just say on average, it goes to theta. Here it says directly the value itself goes to theta. And this, if you divide over here, that's exactly the Chimera bound. So asymptotically, it also achieves the bound. And that's why MLE is super popular. Okay. Everywhere you go, when you do more advanced statistics, you'll see you have a model. How to estimate things? MLE. That at least guarantee is one of the ways, or the way to do it. And backing things up or something like this. MLE is very good, very good. All right. Any question on this? And by the way, this theorem is super important. You see it again and again. For example, in this class, unfortunately, we don't have the occasion to see the power of this. But an example where you see this is in regression. Because the coefficient of beta hat that you estimate in the regression, we'll touch on regression at the end of this class, is from the MLE method. And if you want to say something about the distribution of beta hat, as as the sample size gets large, this theorem is super helpful for you to talk about the coefficient of the regression based on MLE approach. And all regression are based on MLE approach, by the way. So I mean all standard regression. All right. So for your enlightenment, but trust me, this is very important. Any question? All right, so this actually finishes our chapter 10. We have done everything we could for this class in terms of point estimator, okay, and their properties. We will move on to interval estimator and hypothesis testing after this, okay? Those are the other two big topics. But before we do that, let me show you, a simulation that demonstrate the point of the asymptotic. Okay. So this is shared with you on Canvas, but I'm not sure if you remember once upon a time when I was trying to demonstrate to you the idea of the order statistics and how the how the density formula works. I was doing the uniform, That's our go-to example. And I was messing around with the sample size. And I was saying, the max should go, the median, I was demonstrating the median is asymptotically uniform, asymptotically normal from the book, theorem. And I say the max and the min should work in the same way. I was talking nonsense, The max does not work in that way. In other words, it doesn't matter how much you increase the sample size, the maximum does not converge to a normal distribution, as you see, like this. Oops, I think it's too much. Let me just do maybe 200, maybe. Like this, you see? even with the sample size of 200, it does not look normal. Why? Remember, right, this is exactly the exception of the asymptotic that I was talking about, right? The max is the MLE for B, which is 5 here. But because, you know, the derivative, right, with respect to B does not happen for the uniform, the theorem that we say about the MLE asymptotically is normally distributed is not true, right? It doesn't work. Doesn't matter how much you increase the sample size, it will never approach normal. On the other hand, right, here's an easy example. This is the sample variance, right? The sample variance of a normal distribution. It can be the sample variance of other things, but I choose a normal distribution. And remember, right, the sample variance of a normal is the MLE, right, estimator. Actually, it shouldn't be, right? It should be, I think I did it wrong here. It should be not the sample variance. It should be the S prime square. So I should here divide by n rather than n minus 1. Okay. So yeah, it's not the sample variance, the sampling distribution variance. But anyway, right, when I collect the sampling variance, is the MLE, the theory says that as the sample size gets large, it should converge to a normal, right? Or if you look at here, this is exactly the formulation I wrote. The MLE estimator, right? This is this one. Subtract theta 0, but theta 0, right, is exactly sigma square. That's what it's meant to estimate. Times the square root of the sample size, converge to a normal with mean 0 and variance equal to 1 over the Fisher information. So this term right here is the Fisher information. If you look back into the lecture in the previous class, we calculated the Cramér bound for sigma square for a normal population. So along the line, right, we got the Fisher information. This is exactly the Fisher information. Okay, so when I do it like this, so I invert. When I do it like this, then it should be a standard normal. It should be normal 0, 1. So to compare, right, I plot it with the normal 0, 1. So I plot the normalized, right, according to the asymptotic with the standard normal and observe the curve. You see, the two curve is closely fitting. So I should do maybe a little bit more. All right, see? And notice, right, this is not BSing. This is not like saying, oh, I just do something and I fit a curve and it looks close. If I change any of this parameter a little bit, you see that the curve will not be fitting at all, right? So these are really tight. Let me demonstrate by changing this. Like, let's say I got the Fisher information wrong. Let me change it to 4, okay? See? So this is exactly the right way to do it. This is the Fisher information. Again, check me on this, right? Check on this. But you see that is exactly tightly fit because the numbers work out that way. All right. It's an easy case anyway because you know the chi-square distribution and everything. But this shows you that the MLE, right, for the normal, or for when the Cramér bound works, then it is exactly, right, asymptotically normal, with the mean being the true parameter and the variance being 1 over the Fisher information. All right. But when the case where the Cramér bound doesn't work, then you also do not have you don't have the normal asymptotic either. All right, like a uniform. So this should, I hope, serve as a reminder, a counterexample to you, right? That things don't work. You have to always watch out for exceptions when you do like this kind of theorems. Okay, any question? All right, so as I said, right, that's like 1/3 of our journey. We have covered everything we could about estimators. So we're finished, right, with point estimators. All right. So now up next, it's like a show, right? Up next is interval estimators. Or, that's a fancy, that's another way to say confidence interval. Confidence intervals, or CI, okay? Confidence intervals. All right. So believe it or not, I think confidence intervals is something that, most of you have been exposed to when you do some elementary statistics, right? Any introduction to statistics would cover some kind of confidence intervals. So first, right, I think this is 11.1. What is it, right? Some generics, so general ideas. So far, right, we have, let's say, we discussed the idea of theta hat, right, as an estimator for theta, right? And it's very important for us to understand what it means. What do we mean when we say this is an estimator for theta, right? Including it being a random variable with some mean, right, reflecting the biasness, and some variance reflecting the efficiency, right? That kind of thing. But so one of the implication though, right, is because theta hat is a point estimator for theta, what is the probability that theta hat will take on the value of theta? What do you think? Right, I guess this is like a elementary, right, statistics student who see theta hat as an estimator of theta, right, who would say, yeah, actually then theta hat should be equal to theta, right? How often does that happen? This should happen with probability 0, right, or close to it. If you do the usual estimator, right? This is true obviously for the continuous distribution, because theta hat, right, will have a continuous distribution, and to ask a continuous distribution to take on any particular value obviously will be 0, right? I say close to it because you could have a discrete distribution, and in a discrete distribution, maybe by random chance, you may be equal to theta, right? But the point being is a point estimator gives you no room for error, right? Gives you no room for error. In other words, it say this is what I think as an estimator for theta. That's it, right? No room to move around. Again, it's not its own fault. It's just that the method works out that way, and it just depends on what you want to do with it. But of course, if you want to have some room for error, meaning you want some interval, right? So an alternative, right? An alternative is you want some, alternatively, right? You want some, right? And exactly here you see, right? Random, right? Interval, let's say L, right? And here I'll say L depends on X, R depends on X. So L for left and R for right. X is a sample, right? X is a random sample. So that, right, the probability that theta is between this, right? So in other words, is at least 1 minus alpha. So alpha right here, right, is our confidence level. Or, actually 1 minus alpha should be our confidence level. I don't know which one really is called confidence level, but one of these doesn't matter. Alpha usually is like 0.05, right? You know this already, 0.0, 0.1, 0.01, that kind of thing, right? That usual value. So the point is that, right, you want some estimators. So these are, right, these are still estimators because they are, or, if you want, their statistics, right? They are statistics. So they're statistics because they depend on the sample, right? By the arrow here, it means x1 to xn. So here, these are two values that depend on the sample. That tells you that this is what you think is the lowest point that theta can go. This is the highest point that theta can go. Of course, when you make that kind of statement, you cannot make it absolutely unless you make minus infinity to infinity, which is useless, right? But if you make something that is reasonable, then you always make it with some kind of error. And that error is reflected right through alpha, right? So usually I think we try to hit equality here, but like greater than equal is fine, approximately is fine, as you see, right? But the idea is to find 2 points like this so that, right, your theta is smacked in between these 2 random points with some probability, right? And when you can come up with this, then this will be called the a confidence interval, right? Lx Rx, right, is a confidence interval for theta. Okay, and the goal of this section is to find all structure, or how to find a typical confidence interval for a unknown parameter theta. So that's the idea. Any question? So maybe let us do a quick example. Okay, quick example. Let's say x1 up to xn IID normal with mean mu and variance sigma squared. And I think you may have seen this already, but there's a trick, not a trick, but a weird assumption that here we assume that the population variance is known, right? Which is very, very unrealistic. But somehow routinely the literature always teach people like that. So let's do it here. It also works for demonstration purposes. So if you assume that sigma is known or sigma squared is known, doesn't matter, same thing, then this is a confidence interval, right, for mu with 1 minus alpha, right, level. So what do I mean by this, right? What I mean that the probability that this happened is 1 minus alpha. Okay. And notice something. Oh, yeah, thank you. This one, right? I forgot. I'm so used to this, I don't even recognize that I wrote something new. That's the z-score, right? That's the z-score. That tells you, right, that exactly the probability. So basically the probability z bigger than z alpha is alpha. So let's do alpha. So in case you don't see my fish symbol, that's alpha, right? And so basically is that number where the distribution bigger than it is alpha. is a known value, right? Is known value. Don't quote me on this, but I think something like this is true, right? Those kind of like typical values, but you know what I'm talking about, right? You can look it up in Z table. Okay. So the point being is that here, right, X bar is the sample statistic. All of these are known value because I assume sigma square known. Then this is the left point of my confidence interval. And this is the right point of my confidence interval. All right. Okay, so let's stop here and resume on Friday. Okay. If you have any question, I'll answer. If not, then have a good day. You too. Thank you. Thank you. You too.